This is Module 17, find segment lengths in circles. First thing we have to do before we talk about some of the theorems that we're going to be doing, I have to introduce this. When two chords intersect in the interior of a circle, each chord is divided into two segments that are called segments of a chord, and this will become evident with the first theorem that we do. So in this theorem here, I have segments of a chord theorem. If two chords intersect in the interior of a circle, the product of the lengths of the segments of one chord is equal to the product of the lengths of the segments of the other chord. So in this figure, you see we have two chords within the actual circle. To actually find out, and we're dealing with segment lengths, whereas in previous modules we were dealing with angle measurements and arc measures. So in this case, if you take one segment length, for example, AM segment length, whatever it could be a value of x, it could be a number, a numerical value, and you multiply that times the segment length of MB, that should be equivalent to, or will be equal to, ZM's length. So you can do this in another color. ZM's length times YM's length. And again, don't get this mixed up with angle measures and arc measures in terms of degrees. This is actual lengths that you're dealing with. So, with this, let's do an example. So in this, you have to identify what your two segment lengths are for each one of the chords. So I'm going to do this first one here. I have segment length of 8. I have to times that by the next segment length of that chord, which is going to be 6. You multiply those two together. That should be equivalent to the other chord, which is split up into two parts. So we can have 4 is to the other chord length, x. So the main thing to keep in track with this is in terms of algebra, you could have something a little more complicated here. You could have a binomial, which means you might have to use FOIL in some cases. So just kind of keep track of that. But we're trying to find the segment of x, segment length of x. So multiplying this, you get 48 equals 4x. Divide, you get x equals 12. And you're done. So, next theorem, we have secant segment is a segment that contains a chord of a circle and has exactly one end point on the circle. The part of the secant segment that is outside the circle is called an external segment. External meaning outside. And this is going to be evident in this theorem here. I have basically two secant lines that originate from the same exterior point, point P. So if we have two secant segments that share the same endpoint outside a circle, the product of the length of one secant segment and the length of its external segment equals the product of the length of the other secant segment and the length of its external segment. It's kind of a mouthful, but what you need to remember is the PS length, the external segment. So you have PS's length, which is the purple, and then you have to do the entire segment length of that secant line. So the entire segment length of the secant line is going to be PT. And what a lot of people do is they do PS times ST because they relate it to the chords. In this case, you have to make sure it's the entire length of the secant. So once you have that, you go to the other one, which is the external segment here, which is PQ. So PQ I'm going to do in red. And then the entire length of the external segment, which is going to be green, we'll do PR in green. And again, it's the entire length, not the individual segments like in the previous theorem. So, in terms of the application, here's your example. So I'm going to do the top segment because I think it's the easiest one. We have the external segment, which is 7. So it would be 7 times the entire length of that segment. So you're going to have to do a little bit of addition here, which would be 6 plus 7, which would be 13. So that's pretty straightforward. Equals. And this one people usually get mixed up with. So the external segment here is 4. So that's what you're going to start off with, 4. The length of the entire secant segment, What a lot of people say is 4x. But remember, it's in terms of lengths, you're adding the lengths. So we have 4 plus the additional x. That's the entire length. So it has to be 4 plus your x. So in this case, we have 4 plus x, 4 plus x. Once you do this, algebraically solve, do distributive property, and we got, let's see, 91 equals 16 plus 4x. Solve, we got 75 equals 4x, and if you solve for x, you get 8.75, and you're done. Okay, so again, keep track, external segment times the length of the entire segment, and then the external segment times the length of the entire segment, and you set them equal to each other. Okay, and the last theorem in this section, we have secants and tangents in this case. So if a secant segment and a tangent segment share an endpoint outside a circle, then the product of the length of the secant segment and the length of its external segment equals the square of the lengths of the tangent segment. All right, well, what the heck does that mean? So here's your formula. You have your external segment, which is your tangent segment here, which is PS's length. You square whatever that value is. And again, be aware if it is a binomial, you have to use the FOIL or double distributive property. For the secant segment, you have the external segment here, which is PQ. So we got PQ here, which is PQ's length here. Then we got PR's length. Let's do blue. So we got PR's length, which is the entire length of the secant. So whatever that value is, you fill in the numbers, solve for your unknowns. So in terms of the example, you have to first, well, what I would suggest, identify what your tangent segment is. So I see that the tangent segment is x, so that's going to be what I'm going to square. So it's going to be x squared equals, then you look at the secant segment, and the external secant segment part is 6, and you times that by the entire length of that secant segment, which is going to be 6 plus your 4, which is your chord. So once you have that, multiply times 10, and we got x squared equals 60. Take the square root of both sides, you get x equals 7.7 approximately, and you're done. So again, external part of the segment, which is a tangent, you square that, and then take the secant part, the external part of the secant line, you take that times the entire secant line, which in this case is 10. Multiply it, take the square root. Now technically when you take the square root, you should have a plus or minus attached to it, but in this case you don't, because you have a distance that you're dealing with, which is always positive. Alright, so here is just a few examples. So what I'm going to have you do, pause the video and go ahead and work out these examples. Okay, so if you work these out, you should have gotten x equals 12 for the first one, x equals 11.6 repeating for the second one, and for the third one, x equals plus or minus 9, but you only take the plus because you're dealing with distances.